All right, today we are cracking one of quantum computing's most famous cases, Grover's algorithm. But don't worry, forget the heavy-duty math. We're going to unravel this whole mystery with a little help from our quantum detective.
So first things first, what's the big problem we're even trying to solve here? Well, imagine you're looking for one specific thing in a gigantic, completely jumbled up collection of stuff. You know, the ultimate needle in a haystack. Where would you possibly start?
Let's actually set the scene. Think of it like a crime scene. We've got this vast, chaotic database, and somewhere in all that mess is the one crucial clue we need to solve the whole case. But nothing's in order. We're basically fumbling around in the dark.
And I want you to really get the scale of this. We're not talking about sorting through a few files. This could be millions or billions or even trillions of possibilities. When a search is that huge, finding the one right answer can feel, well, pretty much impossible.
So, how would we normally tackle this? Well, we'd call in the old-fashioned detective. This is our classical computer, relying on those tried-and-true, methodical, and ultimately really slow techniques.
The classical detective's method is just exhaustive. It picks up the first piece of evidence, checks it, nope, not the one, puts it down, moves to the next, one by one by one. It's reliable for sure, but you can see how this would take an incredible amount of time.
And that brings us to the biggest problem. If your database has n items, our classical detective might, in the worst-case scenario, have to check every single one. That's n steps. So for 1,000,000 items, that could mean 1,000,000 checks. Yikes.
But what if there's a better way? This is where our quantum detective enters the scene. And this detective, they don't play by the old rules. They come with a toolkit that is straight out of science fiction.
First up is tool number 1, superposition. This is where things get really wild. Instead of looking at one suspect at a time, our quantum detective can look at every single suspect in the entire database simultaneously. All the possibilities just exist at once in this quantum haze. It's like having eyes everywhere.
The second tool is called the Oracle. Now this is the quantum detective's ace in the hole. The Oracle is a special function that can instantly recognize the correct answer. But here's the cool part, it doesn't just yell, hey, it's this one. Instead, it subtly marks the right item by inverting its phase. So think of it this way, every item is like a little wave. The Oracle just flips the correct item's wave upside down, making it unique. It's like an invisible tag that only the quantum system can see.
Okay, so our clue is secretly marked. It has a different phase, but the odds of actually finding it are still the same as everything else. So now comes the masterstroke, making that invisible mark completely impossible to miss.
And this right here is the absolute heart of Grover's algorithm. It's not enough to just find the clue. You have to amplify its signal so it just pops right out from all the background noise. This whole process is called amplitude amplification.
So how does this amplification work? Well, there's a second process called the diffusion operator that takes that one upside-down item and kind of uses it as a pivot. It basically pushes down the probabilities of all the other right-side-up items. And in turn, that boosts the unique marked item way up. The signal from our clue just gets louder and louder and louder.
Now, here's the crucial part. This isn't a one-and-done trick. The quantum detective applies the Oracle to mark the answer, then uses the diffusion operator to amplify it. And this two-step dance gets repeated over and over again, about the square root of n times actually. And with each cycle, that correct answer just stands out more and more. Okay, we've seen the methods, now it's time for the big reveal. Let's put our two detectives side by side and see just what a game changer this quantum approach really is.
And here it is, the classical search takes up to n steps. The quantum search? It takes only about the square root of n steps. I mean, this isn't just a small improvement. This is what's called a quadratic speedup, and it is absolutely revolutionary.
To really let this sink in, just look at these numbers. For a database with 1,000,000 items, a classical computer might need up to 1,000,000 operations. Our quantum detective finds the answer in about 1,000. That is the difference between weeks of searching and maybe just a few seconds. It's a whole different world.
So, after all those loops of marking and amplifying, we finally take a measurement. And because we've jacked up the correct answer's probability so high, when the whole quantum system collapses into one single state, it is almost certainly going to reveal the one clue we were looking for. Case solved.
Now this is more than just a clever thought experiment. The quantum detective skills are in seriously high demand for solving some of the world's toughest problems. Let's take a look at where Grover's algorithm is actually being put to work. Its power goes way beyond just searching databases. It's a huge deal for solving complex optimization problems, like finding the absolute best route for a whole fleet of delivery trucks. It's got massive implications for cryptography, and yeah, that includes potentially breaking some current encryption. And it could even be used to massively speed up how we train future AI systems.
So when you boil it all down, Grover's algorithm is just this perfect storm of quantum mechanics. Use a clever oracle to mark an answer, then you use amplification to make it impossible to miss, and the result is that unbelievable square root of n speedup. And that really brings us to the final thought here. This algorithm completely transforms problems that we once thought were impossibly large and makes them manageable. It's a brand new tool for discovery. So the real question isn't just about what it can do now. It's, with this almost magical speed, what impossible problems are we going to solve next?